Hello everyone. Today we're going to continue on our discussion on vectors from yesterday. So yesterday we defined what is a vector, which there are basically two ways we're going to interpret it. One is algebraically, which basically just means is a list of numbers. And another way is geometrically, which would represent it more as a arrows that pointing from one point to another point. So what we're going to talk about today would be to talk about some operations. Now that we define this object, this mathematical object, whether we define it algebraically or geometrically, but it's a mathematical object. Now what we want to do is try to see if we can do algebra with it. And in order to do any kind of algebra, we must define operations. So we're going to define some very basic operation, and these operations are similar to operation that you first learn in math, like addition and multiplication. But because of the fact that we're dealing with vectors which have more than one numbers involved, we have to kind of learn how does that change the way we define some of these operations. And for the most part, they stay relatively the same. But in some cases, the way we interpret what this operation, well, what those operations do, would be different. So we'll get to that in a little bit. So let's start. So we're going to try to define what we call vector operation. So just a quick recap. A vector for us is an ordered list of numbers, and it's defined by how many numbers in the list, and we can say that it exists in R2, R3, R4, and so on and so forth. And compared to that, a scalar is just one single number, which we would refer to as in R1 or just simply R. And of course here we only talk about everything in real numbers, so nothing about complex numbers, imaginary numbers, or things like that, just regular numbers. Okay, scalar. Okay, that look a little bit better. All right. So what are the two basic operations that we're going to try to, what are some of the basic operations that we're going to define? So the first one is very simple, would be how do you add two vectors together? So let's define the operation. So the next thing we're going to talk about, or the first thing we're going to talk about, the first operation we're going to talk about is called vector addition. So how does vector addition work? Well, it actually works the same exact way that you think it should. So let's define it mathematically first. So let's say given two vectors in Rn. Now, before we move on, several things I do want to point out that are important and help you understand how some of these math, how they're defined properly. So in here I say that to define this operation called vector addition, I must start with two vectors in Rn. Now that might sound simple, but that already conveys quite a few different ideas that you need to pay attention to. Number one, it defined that this operation is a binary operation because it can only be defined when you have two vectors. So binary operation is an operation to combine two objects into one, and that's what this is. And two, because both of these vectors must be in Rn, therefore identify that these two vectors must have the same same numbers inside the vectors. They cannot have one cannot have three numbers in it and the other one have four numbers in it. Then that would not work. They have to have the same number of different number within the vector. So in here we go generically define these two vectors. So I'm going to call one of the vector, now here be careful, I'm going to call one of these vector x. So x is the name of the vector. So then what I'm going to do is I'm going to say, well, vector x would be just x1, x2, dot, dot, dot to n. Now notice that in this scenario right here, I'm using a subscript notation. So I'm calling each number inside the vector using the same letter, in this case x, as the vector that's being called, which is vector x. And then the subscript indicate the basic position within the vector. So x sub 1 basically refer to first number in the vector x, x sub 2 being the second number in vector x, and then x sub 3 will be the third number in vector x, and on until the nth number, which is x sub n. And I'm going to similarly define a second vector. I'm going to call the second vector vector y. So that will be y sub 1, y sub 2, dot, 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 to y sub n. So please do not confuse this with the xyz notation. Xyz notation would use x, y, and z to define first, second, and third position within a vector. Here we're not using that. We're using a subscript notation. So then how do we define an addition between these two vectors? So now we can then define the following. Then if vector z is equal to vector x plus vector y, then this is what we know. Then vector z would obviously equal to z1, z2, zn, where each z sub k is equal to x sub k plus y sub k. So what does it mean? This all looks very mathematical, and it is. And as I always like to say, mathematicians like to write things that are very confusing for people to look at so that people don't understand what it is and make them look smart. So what does it basically tell me? It's actually telling me something very simple. It basically tells me that if you want to find out what z sub 1 is, well, guess what? Z sub 1 is the sum of x sub 1 and y sub 1 together. Makes sense because x sub 1 and y sub 1 are in the same position within their corresponding vector. So when you add the two vectors together, you're supposed to add the two corresponding number together. And then what is z sub 2 going to equal? Well, z sub 2 is going to equal to x sub 2 plus y sub 2. And then so on and so forth until you get to the last one, which is z sub n, which has to equal to x sub n plus y sub n. So this statement right here, it's just a fancy way to say that when you add these two vectors together, you add the corresponding number together. And you cannot add two vectors together unless they have this equal pair of corresponding number. And if somehow they don't have a pair, then you can add the two vectors together completely. Now, show you a very simple example. And you find out that doing this is like nothing more than just doing a whole bunch of addition at the same time. So suppose I define the following. Let's say given vector x is equal to 1, 2, 3, and let's say vector y is equal to -1, 2, 5. Well, then what happened is, then if I do vector x plus vector y, then that will mean 1, 2, 3 plus -1, 2, 5. And so how do I add them together? Well, we add the pair together. So it becomes 1 plus -1, 2 plus 2, and 3 plus 5. And guess what that come out to be? Well, that come out to be 0, 4, 8. There you go. That's the sum. Now, once again, it seems like a very simple problem, and you are essentially doing nothing more than a whole bunch of addition in one single problem. But there are a lot of things to pay attention to. So let's talk about them. So first of all, I want to call to your attention, and these are little things that if you don't pay attention to them now or don't learn to pay attention to them now, you find out that throughout the entire school year, you're going to struggle. Because a lot of these little things rely on pay attention to. A lot of the problems that you have to do in the future rely on you to pay attention to these little things. It helps you understand what you try to do. It helps you how you understand whether your answer makes sense. So in here, pay attention to the following. Look at vector x and y. Notice that they both have 3 numbers inside. Okay, so therefore identify that both of these vectors are in R3. Makes sense. You have 3 numbers inside a vector, therefore you have, technically speaking, 3 real numbers that you have to represent, and so therefore it's called R3. The R stands for real. The number 3 indicate that's 3 of them. Okay? And now when I add them together, notice what the outcome is. The outcome is right here, which is also a vector in R3, which makes sense. Because if you're adding 2 vectors together, they're both in R3, you're basically adding 3 pairs of numbers together, and therefore give you 3 result. And therefore would give you a vector in R3. Now, this might seem like so obvious, and it is very obvious, but it's actually a very important mathematical concept called closure. Closure basically define the following. It basically means that when you apply an operation to multiple objects, in this case 2, because the operation we define is binary, if those 2 objects are of the same type, in this case the type is R3, then the resulting object must also be the same type, which also in R3. So in this case, we'll say that vector addition is close. Or another way to say it is that it has what we call the closure property. Now, you might be thinking like, wait a minute, that seems like almost everything that we do have this kind of property, right? And surprisingly, the answer is no. Okay, there are actually a lot of operations that does not have closure property. So in order to understand this, I can give you some very simple example, and you can definitely write them down if you want to, but if you simply listen and try to think about it, it will make sense to you. So in order to understand, first of all, closure require you to define an operation, very likely a binary operation, but it could actually be a single operation on one object. And also have to define on a set of numbers to work with. So in this case, we're saying that vector addition is closed with basically what we define as vectors. So can vector addition not be closed if it's defined by some other type of things? And yes, it could. So give you a very simple example. Addition between real numbers are close. But addition between 2 odd integers is not close. Why? Well, because if you think about it, if you add any 2 real numbers together, the number that you get would always be a real number. It can be imaginary somehow, not through addition. But if you add 2 odd integers together, then you actually would always get an even integer, which is not the same as odd integers. So therefore, addition, as simple as addition as a basic operation, is actually can be closed under some group of numbers, but not closed on some other group of numbers. So in here, vector addition is definitely closed if you're adding 2 vectors together. But if you define vector addition on some specific vector, then it might not be closed. So keep that in mind. Now, what's important about having this closure property? Well, closure property is actually very important. The reason why it's very important because the following. What we define here, vector addition, is a binary operation, meaning we only can add 2 vectors together. But of course, here comes the big question. What if we have to add 3 vectors? Well, now we can use a binary operation to do that because binary operation is combine 2 vectors together, not 3. But lucky for us, because vector addition have closure, therefore if we have to add 3 vectors together, then the proper mathematical way to do it is to add 2 out of those 3 vectors together first and have a result. And the resulting single vector would now be then add to the third and remaining vectors to form the sum of 3 vectors. And this process can be applied repeatedly to add any number of vectors we want. So the only reason why we're allowed to actually add more than 2 vectors together through vector addition is because vector addition has closure. And if it doesn't have closure, we're stuck with only allowed to add 2 vectors together. So keep that in mind. It is very important properties. So the next operation I would like to define is this one. Scroll down some more. Okay, here we go. Okay, the next operation I want to define is called scalar multiplication of vectors. So this, as the name suggests, is some kind of multiplication, but it's actually not multiplication that you think you're learning, because this is called a scalar multiplication. So this multiplication actually involves some kind of scalar involved. So let's define what it is. So let's say we're given a vector in Rn. Let's say vector x is equal to x1, x2, dot, dot, dot to xn. Now, important to notice that this say given a vector, 1, not 2. So therefore tell me that this is actually not a binary operation. It doesn't combine two vectors together to form a new one. So a little different than vector addition, which is a binary. But because this is a scalar multiplication, I do need a scalar. So I'm going to go and say, let's say given a scalar, and I'm going to call this scalar S. Then what happened is the following. So if z, vector z, is equal to S multiplied by vector x, then this is what basically means. That means that vector z is equal to z1, z2, c2, dot, dot, dot to zn, where each z sub k is equal to S multiplied by x sub k. So understand, it's a very fancy way to explain some very simple concept. So this basically is saying that if you take a vector and you multiply by a scalar, a number in front of it, or behind it, actually it doesn't matter. But if you multiply by a number, what you're supposed to do is simply distribute that number that you multiply into each of the number inside the vector. So in this case, if I want to find out what z sub 1 is, I just basically take x sub 1 and multiply by the scalar that we multiply with. And that's all. So I'll give you a very simple example. So here's a very simple example. Let's say we're given that vector x is 1, 0, negative 3, 7. Okay. Then 3 vector x would just be equal to 3 times 1, 0, negative 3, 7. And that should become 3 times 1, 3 times 0, 3 times negative 3, and 3 times 7. And so that just equal to 3, 0, negative 9, 21. There you go. That's your answer. Notice that the answer is a vector in R4, and our original vector x is also in R4. So therefore tell me that this operation, scalar multiplication, is also close. So scalar multiplication of vectors is also close. If we apply these two vectors and scalar. Good. Now that we define these two properties, these two operations that allow us to actually do math, the next one I want to talk about will be the following. These two operations, based on the way that they are defined, would definitely have some properties that we can talk about. And what does it mean by properties? Properties of an operation usually define some ways that we can do these two operations without changing the outcome. So all of these properties basically tell me that, oh, you can do it this way or the other way, and guess what? Both ways give you the same answer. And that's what most of these properties does. And they allow us to simplify expression and allow us to combine things easier way, because we know whichever way we do it, we get the same answer. So there are quite a long list of properties that I want to define for you. And once we define all of them, you can then kind of use them in doing your problem. We also go talk about proving some of these, and you will be asked to prove some of these properties on your next test. So make sure you pay attention to when I explain to you how to prove them and what would be important when you're proving these property, because you want to make sure you understand what the expectation would be when I ask you to do one of these proof. You don't want to write too many steps because who want to write more than what you need, but also don't want to write less, because if you write less, I would have no choice but to take points off. So you don't want me to do that either. So next we're going to talk about would be properties. Basically properties of vector addition and scalar multiplication on vectors. All right. So I have 9 properties that I want to talk to you about. So we're going to just stay all 9 of them. And then we're going to probably try to prove 1 or 2 of them in today's video. And then that would be it for today. Okay, so just a little bit more and then we'll be done. So let's state the properties first. So here are the properties. So before we start, let's set up first. So let's say given 3 vectors in Rn. And what are those 3 vectors? Vector x, vector y, and vector z. So that off the top, immediately it tells me that all these probably only apply when vectors have the same dimension. So if you have different vector with different dimension, then these properties would not be applied. Next, let's say we are given 2 scalar to work with. So let's say in this case, the 2 scalars are R and S. Okay, so here comes some of these properties, and some of these properties actually have a name that you, if you want to write them down, you can definitely write them down. Excuse me. And it's not any new name that you haven't heard before. Most of these you probably heard before, and if I write them down, you can probably already guess what they're called. So number 1, property number 1 states the following: if you have R times vector x plus S times vector x, then that just equal to R plus S times vector x. Now, once again, a lot of these things are very important, and they're very minor, and sometimes students don't pay attention to them. But I like to point them out because they are important, and if you pay attention to them and understand them, it just makes everything so much more clear when you try to get into things that are confusing. So first of all, some things I want to point out. Number 1, this is what we refer to as an identity statement, because this statement is always true regardless what R, S, and vector x are. Okay, so if an equal sign between the left side and the right side, basically saying that the left and the right are always the same, no matter what you choose, R, S, and vector x. Good. And somebody can probably identify what this property is. This is actually called distributive property. It's scalar multiplication distributive property. Or in some cases, you can think of it as a factoring property, depending on which way you look at it. If you look at it from the left side to the right side, is more like factoring, but if you look from right side to left side, is more distributive. And what's important about this property? So important to understand how all these properties work. All these properties basically tell me that you can do things, as I said before, you can do things one way or the other, you wind up have the same result. That's what all these properties tell us. So what does this particular property tell me? Well, tell me is the following. If you look on the left side of the equation, right here on this side, it basically tells me that I have to do 2 scalar multiplication first, one R times X and the other one is S times X, and then add them together. So very important, because math is always about applying operation in orders. As a matter of fact, one of the first things that you learn when you first learn about math is called order operation. You have to understand when you have a whole bunch of things that you have to do in math, how do you do them in the correct orders? Because some cases, many cases, if you do them out of order, you get the wrong answer. And that is the reason why properties like these are extremely important, because properties like this tell me that you can do things in different order and you get the same result, and therefore meaning that when you do things you can sometimes pay less attention to what order you do them because it wound up being the same. So this probably tell me the following: the left side requires to do the scalar multiplication first, there are two of them, and then vector addition, and that will give you the result. What happened on the right side is that the right side tell you like, whoa, you can actually do this first, which make it easier. You can actually do just adding the scalar first and then do the scalar multiplication. So notice the order of operation is reversed from the left side to the right side. Left side, you do scalar multiplication, then vector addition. The right side, you actually do the addition first between the scalars and then do the multiplication. So that's the power, that's the important part of this property, is to tell you that if you're dealing with scalar multiplication and vector addition, really doesn't matter which way you do them. If you choose to do it the other way first, you are okay. Or if you choose to keep it the same way, you're okay too. So that's important. That allows us flexibility when we evaluate an expression, and we can now choose which way we want to do that's easiest for us. Okay? And you see the same exact concept for almost all of these properties. So property number two is this. What if you have r times vector x plus r times vector y? So in this case, this basically tells me once again do two scalar multiplication first and then add them together. And what this probably basically says is that, well, you can actually add the two vectors together first, vector x plus vector y first, and then multiply by r. And once again, this is also called a distributive property or factor property, depending on which way you look at it. Number three, suppose you have two scalar. You have r and you want to multiply by s times vector x. Well, this basically tells me that you have to do this scalar multiplication first and then do a second scalar multiplication. But you could actually multiply the two scalar together first and then multiply by the vector. Now, important to understand that in this case, this is not distributive property. This is actually more similar to what we call associative property, meaning they can choose when you multiply multiple things together which two to multiply together first. So in here you multiply three things together, two scalar and a vector. You can either choose to multiply one of the two vectors by the one of the two scalar by the vector first and then multiply by the second scalar, or you can actually multiply both scalar first then multiply by the vector. And in this case, this probably tells you that either way you get the same result. Be very careful. Do not kind of distribute the r into both s and x because that would be wrong math. You only do distributive property when you have a multiplication with an addition. Okay? Otherwise, you really don't distribute. Okay? Not in this sense. Number four. Number four says the following. When you take vector x plus vector y, well, guess what? It's the same as vector y plus vector x. And a lot of you can identify this is called commutative property. Number five. What if you want to add three vectors together? Let's say I want to add x, y, and z together, just like what we talked about. What will happen? Well, you can't add three vectors together because we define addition as binary. So therefore, we have to add two of them together first, then add the remaining. So you could, associative property, basically say you could add x and y first, then add z. Or you could add y and z first, and then add x. Now, I know some of you probably also thinking, well, can I add x and z first, then do y? And the answer is depends. In order for you to add x and z first, it requires you to rearrange our summation right here. Instead of x plus y plus z to become x plus z plus y. And that is only true, you can only do that if property number 4 is true. You have commutative property. Because if you reverse this to write x plus z plus y, you're basically telling me that z plus y is the same as y plus z. And that is only true in some cases for some operation in some numbers or some objects. So therefore, you cannot always assume you can do that. So this is probably better way to write it. And you could write x plus z plus y, but that's only true provided you know 4 is true. And I would not write it because it's not always true for all operation. To define the next three properties, I have to define a new vector. So I'm going to define this vector. I'm going to say let the 0 vector be the vector that has only 0 in it. In this case, 0 vector will be in Rn because otherwise it would not make sense for all the operation to be defined. However, the 0 vector is usually defined without a dimension because it usually would define to just have whatever dimension it is. That will make the math work out. So meaning that if you're adding two vectors in R4 together and you get a 0 vector, then the 0 vector is assumed to be in R4. It will not be in any other dimension other than in R4 to make the math correct. So in here, same exact way, 0 vector in this scenario assumed to be in Rn because that would be the dimension that make all the math work. And there are three properties relating to 0 vectors. The first one is this one. If you take any vector x and you add the 0 vector to it, well, guess what? It just stays the same. So in this case, notice that the 0 vector actually kind of behaves the same way as 0 in our number system. It's called additive identity. And what does that mean by additive identity? Additive means addition, and then identity means stays the same. So meaning that when you add 0, things stays the same. Number 7. What happens when you add vector x to something called negative vector x? Well, that gives you the 0 vector. And this is called the inverse property for addition. And the vector negative vector x is basically -1 times x. Is called the inverse of x for addition. Okay, and sometimes called opposite x. And number 8. What happens if you take the 0 scalar multiplied by vector x? Well, 0 times anything do equal to 0, but in this case, because of the closure property, it dictates that if you multiply 0 times any vector x, you get the 0 vector. You don't get the scalar 0 because scalar multiplication have to be closed, and therefore when you multiply a scalar by a vector x in Rn, your result must be a vector in Rn, and therefore in this case become the 0 vector. So be very careful with that. Don't write down 0 without the arrow on top in this case, because then I have no choice but to mark it wrong. And the last property is property number 9, which states the following. If you multiply the scalar 1 by the vector x, well, you just get vector x. Now, unfortunately, I think this video is long enough. It's about 33 minutes so far, and I don't want to make any video too much longer than 30 minutes or so, because I want you to be able to, if you need to, be able to watch it in class and have some time in the beginning and the end of class to do whatever you need to do. So I'm going to stop right here. So tomorrow video, what we're going to try to do is to talk a little bit about how some of these properties are being used, and also I'm going to try to prove some of these properties for you. And that will be for tomorrow. So I think that's it for today. Talk to you guys again tomorrow. Bye.